Hello, space fans, and welcome to Professor Britton's Wacky Universe. Okay, space fans, I couldn't help myself. Can you see me okay? Can someone see me okay? Give me a thumbs up. Wow, there's so many of you. I can see all your little faces and all your little windows. I love it. Okay, well, hold on a second. My computer was going nuts there. Okay, so welcome to our first online Astronomy 1010 class. It's so nice to have you guys here with me. I just want to make sure, can you guys hear me okay? Everyone can hear me fine? All right, I'm getting some thumbs up. I like it. So yeah, I had you guys mute yourself because it was a little cacophonous out there, but feel free to chime in with questions or, oh, whoa, someone just gave me a thumbs up. How did you do that, Elena? That was cool. Anyways, just feel free to unmute yourself and comment. Damn, okay, I like these thumbs up. I don't know how you did, oh, reactions, I see. Let me give you one, there you go. Okay. Now, at some point, we're going to try to give you guys some notes on the note board. I'm trying to make this as much like our class as it was at CCRI. So I think from experimenting with friends that I'm going to need to move the board a little bit closer when it comes time for notes. So we'll get there. I guess all of you guys are here because you got the email and you know that we're going to try to do our lectures. Hello, everyone. We're going to do our lectures as usual at 11:30 on Mondays and Wednesdays. The night class should be joining us. I can see Tina there. Hello. Let's see. The plan, if you can remember it, is for us to do our lecture from 11:30 to 1 or so. Try to make that interesting. And then afterwards, on Mondays, we're going to do our lab all together. The lab is going to be a little bit janky. I'll have some setups here. And let me see if I can show you what's going to happen. I'm going to share my screen. I can share my iPhone with you, and that's how we're going to take data measurements for the lab. Let me try this. I'm going to share my phone and just make sure. What? A plugin. Okay, this was working the other day. Let's just see. I'm still figuring all this stuff out. Oh, rats. Okay. Well, that's a little scary. So for some reason, my iPhone sharing device has failed, which it did not do on any of my 3 tests. Let me try this one more time. Nuts. Okay, so we might have to restart before the lab anyways. We'll see. If it comes time where I need to show you a demo through my iPhone, we'll get there. Anyways, during the lab, I'm going to have a little setup here in my apartment, and I'm going to try to show you guys some measurements, and you guys can just kind of write down the values. I don't know if you saw on Blackboard, but I have a worksheet for you guys to download on spectroscopy. So at some point, if you can download it, if you have a printer and you can print it, cool. If you can edit it and make some colored lines in something like MS Paint, that would work. And you could also try to draw out, if you don't have a printer, you could even try to draw out the spectrograms and kind of make a hand-drawn version. Diana, did you have a question or were you just stretching? Oh, you're just stretching. Okay. All right, everyone's still kind of muted here, so. All right.
No, I was just getting my charger for my laptop.
Oh, I see. Okay, all right. Okay, well, it's nice to have all of you here. I talked with Jillian before the class started, and she told me that last time we ended up having a discussion about energy. We did potential energy, we did kinetic energy, and temperatures. Is that correct? You guys can give me some thumbs up or something. Is that what we remember? Okay. So I think today what we're going to try to do is we're going to try to tackle this. Oh, thoughts? What?
I don't know if the night class went over that stuff. Because I know
yeah, that's a
we
good
were a
point.
week behind.
No,
We
the
did
night
not.
class. Did any, Tina, did the night class, do you have a last notes for us, Tina, from our class? Let's see where the night class ended up. They must have at least done energy. Okay, well, nothing or?
Escape velocity, I think, was what we last did.
Oh,
Yeah, that's
brother.
what we did.
Still on chapter 4.
Yeah, okay, so the night class is a little behind. So for the night class, we're just gonna wing it, okay? The potential and kinetic energies, I can throw them up on the board in a few moments here, but what we're gonna do today is, yeah, I'd say for night class people, just let us pass over that for now and we'll come back and get you guys later, okay? I think the goal today is to start with atoms. So let's see, I don't think any of the classes have done. Let me kind of pull my stupid screen closer here. And I'm gonna try making some notes and I wanna see if you guys can read any of this, okay? So, how does that look? Can you guys read that? If you can't, you gotta let me know. Yeah, you can see that? Okay.
Yeah, that's pretty good. Yeah.
Matthew says it's okay. Pretty good. I spent a lot of time futzing around with the light, and the problem is certain directional lights add a lot of glare. Let me see if I can do this. A little more light. I'm kind of looking in my little tiny window here, so it's tough. Okay, so one thing I want to do is hopefully, even though the share iPhone doesn't work, my share screen should work. And I want to point out to you guys that in Blackboard, I've shared all of the PowerPoints with you. Did you guys notice that I had the PowerPoints? Well, I'm going to try to refer to the PowerPoints at key moments here. Now that I think about it, I probably should have queued that up beforehand. So let me see. I'm going to share my screen with you. This is my computer screen. And thank God, at least that works. And I'm just going to go to my 1020 lecture because I like the light and telescope there. I'm a little better. Okay, so I'm hoping if I do function F5, you guys, where are we here? You guys should be looking at a picture of the Bohr model of the atom. Do you see that, Tony? I can see your face right now, Tony. You can see the Bohr model? Okay. So the Bohr model, named after Niels Bohr, is a model of the atom where it sort of resembles a small baby solar system. And you can see we've got a nucleus. Can you guys see my mouse as I point with my mouse? Just, okay, cool.
Yes.
Yes.
Awesome, rad. So I'll point with my mouse here. We've got the nucleus inside the center of the atom. That's made up, of course, of protons and neutrons. And then we have electrons going around it in a little baby solar system. Now, I'm guessing you guys have heard of protons, neutrons, and electrons before. This is pretty basic stuff here. But I want to throw some notes on the board, things that you might not have known about, some terms that I'm going to be using all the time that I want to make sure you're conversant with. So if I can go back to my screen here, let's take some notes. So we're going to make a model of a simple basic atom called helium. This is an atom I'd like you guys to accidentally memorize eventually. And I'm going to start by drawing two protons in the center. So let's see here. So I've got 2 protons. I've got 2 neutrons in the center. And I'm going to draw 2 electrons in blue going around. Here's 1, and here's 2 little electrons. Please let me know if you guys can't hear me or if something gets weird. All right. So you can put this right into your notes. We'll start real basic. So we have our electrons, which are negatively charged particles. We have protons, and we have neutrons. It's time for us to learn a new vocabulary word together. The protons and the neutrons together are what people call nucleons. Can you guys see that? It looks like you can see it. Nucleons are protons or neutrons. Sometimes you want to refer to either one of these things. Okay, let's talk a little bit about these particles and let's define a couple of new vocabulary words. I don't have a ton of board space here to work with, guys, so bear with me as I get through this. I'm going to take down a couple of different notes here. The first thing I want to define is something that I'm going to call A. Can you guys hear me when I turn my back to you? I know this microphone's kind of crappy. Not
No,
so
I can
good.
hear you.
All right, I got to try to remember to talk at the screen here. Okay, so A is going to represent the atomic number. And the atomic number is the number of protons in the atom. The atomic number is of extreme importance in all of chemistry and science because the atomic number defines the element or the atom. So the atomic number defines the element or the atom. Let's go ahead and share my screen with you for a second. Share screen. Let's see if we can get that slideshow back up here. Come on, baby, give me access to this. So here you can see the periodic table of the elements. Tina, give me a thumbs up if you can see the periodic table of the elements, because I can see your face right now. Okay, good. I just want to make sure this thing is working. The number in the upper left-hand corner is the atomic number, and it defines the atom. So hydrogen has an atomic number of 1. Lithium has an atomic number of 3. You'd think this was obvious, but it's going to turn out that as we take and remove and add little particles to our atoms, it can sometimes get a little confusing which atom we are dealing with. By defining the protons, by defining the element in terms of the number of protons, we make sure we have a clear definition between one atom and another. Okay, let's get back to my chalkboard here for a second. The next thing I want to share with you guys is what I'm going to call letter M. And letter M stands for the mass number. The mass number of an atom is the number of nucleons. So it's the number of nucleons in my atom. That means it's the number of protons plus neutrons. The number of protons plus the number of neutrons. Can you guys read all that? Okay.
Yeah, it's pretty legible.
Pretty legible. Yeah, I know it could be better. I ordered a new fancy camera, which I'm hoping will improve the quality of these lectures, but today we're doing it webcam style, so it's going to be a little rough. Okay, the mass number defines the isotope. So the mass number defines the isotope. That is, it is the total number of, sorry, I've already defined it that way. It defines the isotope. An isotope means this. It means same number of protons, but a different number of neutrons. And in a few seconds, I'm going to give you guys a couple of different examples of atoms with different numbers of protons and neutrons. Okay, one other thing that we need to talk about is the charge of these particles and how atoms work. Atoms that are equal numbers of that have equal numbers of protons and electrons are called electrically neutral. So let's add that next. I think I'm getting, let me just use my hand. I think that's the bottom of my screen, so I'm going to have to go back up to the top here. Okay. Atoms are normally electrically neutral, and that means the same number of protons equal to the number of electrons. And we'll talk a little more about being electrically neutral in a moment. I just want to get all the definition stuff down into your notebooks. Atoms are normally electrically neutral, but it's possible to add and remove electrons. And when you do so, the atom becomes ionized. An ionized atom is one in which you remove, or in some cases add, some number of electrons. When you do this to atoms, when you cruelly add or remove electrons, you create a new state of matter known as a plasma. Ionized atoms constitute a plasma, which is basically a charged gas. That's the fourth state of matter, and we're going to be talking quite a bit about plasmas as we learn about not only the sun and its outer layers, but also the layers of planetary atmospheres, which I hope to God to get to before this shit show ends. The layers of planetary atmospheres also contain certain amounts of plasmas. So we're going to need to study them. Okay, so now I want to get some thoughts from you guys here. I want to just kind of go back to my share screen for a moment. And I want to show you guys that Bohr model of the atom again. Let's see if I can control this thing. Okay. So here we see some electrons going around the nucleus, kind of like a little baby solar system. That's what's the hallmark of the Bohr model of the atom, is that it kind of looks like a bunch of simple charged particles orbiting around each other. And the electrons actually do orbit on Keplerian ellipses, if you remember what the hell that is from your mechanics section. Why do the electrons orbit the nucleus? Well, if I asked a stupider question, what if or Tony, maybe you want to weigh in? What's making the electrons go around the nucleus?
I would say because the nucleus actually has mass, while the electrons have very little mass, and
Well, I guess I'm thinking, buddy, I'm thinking in terms of
something like that.
Huh? Okay, let me try this again. If I asked you what makes Earth go around the sun, what causes Earth to orbit around the sun, what would be your answer to that question?
The gravity of the sun.
That's what I wanted to hear, Zach. Thank you. Just gravity, right? So I guess the thing that I'm awkwardly trying to push you guys to answer is it gravity that's making the electrons orbit around the nucleus? Because Tony, you said something about mass, and mass makes me think about gravity, you know?
I mean, yeah, I can't remember my quantum mechanics that I learned on science one time, but I would say gravity probably doesn't apply like it does in our world here.
Yeah, technically speaking, there does exist a force of gravity between these particles, but their masses are so absurdly small that gravity doesn't actually bind the electrons to the nucleus. I was wondering if anyone did know what the force was. This is just kind of me figuring out what the crap you guys know, you know? What's the force that, Kirill?
Electromagnetic force?
Yes, electromagnetism. Woo woo. Okay, so let's have a little discussion about that. Let's get back to our board here. So I just wanted to make sure that someone had heard of electromagnetism. It's okay if you haven't. I'm going to go to my speaker view here. My speaker view. Oh, now I see Kirill's big face. How do I get to me? Okay. I guess speaker view isn't working for me. All right. Let's take a couple more notes here. I want to show you something that you might not have learned in a basic science class. Let's start with a simple note up in the top. Atoms are held by electromagnetism. Electromagnetism is a new fundamental force of nature. And electromagnetism is based on a carrier called charge. charge is a sort of abstract fundamental property that little particles like protons and electrons have. Let's make a little table that I think you guys might find interesting. If you have a ruler at home, you might want to have one handy for some of these lectures. You know, I love tables and graphs and charts. So I'm going to go ahead and kind of make a tic-tac-toe box here. Oh, that kind of worked out. All right. Actually, let's see. Stay with me. Stay with me, people. Okay. Actually, I'm going to make one more. I'm just going to point to this and see if you guys can see everything. More or less. All right, let's try to fix this. Okay. So in this column up here, I'm going to put my particle. I'm going to list its mass, and I'm going to list its charge. And the first thing I'm going to do is I'm going to draw myself a big fat proton, the positive charge. I'm going to draw myself a big fat neutron. And I'm going to draw myself in the bottom here a little tiny electron. And I want to start with the electron. The electron has an absurdly small mass. The mass of the electron is basically 9 times 10 to the negative 31 kilograms. That's a pretty small, stupid number. Now, if I were to also write the masses of the proton and the neutron in kilograms, the numbers would also be equally stupidly small, well, not equally stupidly small, but stupidly small enough that it would be difficult to pay attention to what's going on here. So I'm going to write down the mass of the proton and the neutron in terms of the electron instead. Let's call the electron's mass 1 electron mass. There's a new unit for you. Compared to the mass of the electron, a neutron is 2,000 times greater. So if you're just thinking about mass, the mass of a neutron is significantly more massive than the electron. And by a curious coinkydink of nature, the mass of a proton is also roughly 2,000 times greater than the electron. Let's write that down. Can you guys read that? Give me some of those thumbs ups if you can read it. Okay, cool. If you're having trouble reading stuff, you got to let me know so I'm not just scratching. Okay, I'm seeing lots of Samantha, Francesca, thank you very much. Okay, you know, man, this gets me thinking about something. Remember this guy? It was a lot more fun when I could show it to you in class. This is my 1 kilogram test mass. I brought everything with me, by the way, in case you want to see here. I've got the whole cart here. I strapped it into my van with bungee cords and I just drove it home with me, okay? I brought the whole kit and caboodle. My apartment's a disaster right now. Okay, so what is mass? I think at some point we had a discussion of mass versus weight. But does anyone remember what the definition of mass is? Or could you tell me, because you just know shit about nature? What is this stuff that we call mass? You think you know what I'm talking about, right? But what am I talking about? Does anyone know what mass is? Oh, I can see lots of chats happening. It's hard to tell. Oh, look at this. This is live AF. I love it. Okay.
How much
right,
matter there is in something?
Oh, I'm sorry, Kirill. Can you say that one more time for me?
How much matter there is in like something?
Yeah, it's a measure. Let me see. I want to stand back so you can see my whole stupid head here. It's a measurement of the amount of stuff in stuff, right? Kirill says mass is a measurement of the amount of matter. Now, I want you to go on a little thought journey with me, Kirill, because The more you think about that as a definition, the weirder and weirder shit starts to get. For instance, if this is a 1 kilogram mass, 1 kilogram is somehow measuring the amount of stuff that's in this test mass. And I guess if I cut it in half, I'd have half a kilogram. And if I cut it into 10 parts, I'd have 1/10 of a kilogram. And as you cut it down into smaller and smaller bits, you're measuring smaller amounts of mass and smaller amounts of matter. So at first, mass is something that seems pretty obvious. It's a measurement of the amount of matter. But if you continue to cut this little bastard up into smaller and smaller pieces, eventually I suppose you'd get down to the molecular or even the atomic level, and then you'd be left with this. Except this is a lie, it's a false picture, because you can see from our previous notes that the neutrons and the protons are 2,000 times more massive than the electrons. And another thing that's a lie about this picture is it doesn't really show you the size scale of atoms, because the orbital radius of the electron is much, much bigger than any of the particles. If you actually tried, oh, I know, I'm gonna do something funny here. Bear with me. If I'm gonna share my screen and go to the digital whiteboard, so I wanna keep that stuff up here. Let's see if this works. I gotta hide you guys. Okay, hold on. If you actually tried drawing an atom to scale, your nucleus would be like this little dot, and then the orbit of the electron would be like, in fact, this picture here doesn't even do justice to it. Can I erase? Yeah. Oh, no, that's not erasing. Well, shit, guys. You're gonna have to bear with me as I figure out how to do this. Oh, it worked with my finger. Okay, well, whatever. The nucleus would be so incredibly tiny in comparison to the orbit of the electron that you wouldn't even be able to see the electron. What the hell is my point? Do I have a point here? My point is atoms are mostly empty space. There's mostly nothing there. So if we're talking about mass as the amount of atoms that's in a material, you start to realize that we're talking about the mass of the atom itself. But the mass of the electrons kind of don't matter in comparison to the mass of the protons and the neutrons, because they're 1/2000. Okay, so I guess when we're talking about mass, what we're really doing then is we're measuring the amount of stuff in a proton or a neutron. Here's my proton and my neutron, right? So mass, what it really is it's the amount of kilograms that's in one of these things. The problem with this picture is that the proton and the neutron aren't actually particles. They don't look like this. We imagine things as balls because balls are the kind of things that we understand, right? They can hit us off the head, they bounce off our noggin. But in reality, when you get down into the world of the microscopic quantum world, protons kind of behave more like energy packets or some kind of wiggling dispersed clouds of energy. So what the shit are we talking about when we talk about mass? In fact, you start to realize that we probably understand the force of gravity better than we understand what mass is. Mass is actually sort of an abstract concept. And today, most modern physicists, they think about mass, I'll try to write it up here, as the carrier of the gravitational force. I don't know if you guys can read that. That might be too small. The carrier of gravitational force. We actually define mass in terms of the force of gravity because the force of gravity makes more sense to us than what mass is. Mass is some sort of abstract property that these little particles have. Why am I telling you all this? Because charge is a similarly abstract property. Charge is a carrier of the force of electromagnetism. Tony, I think I need a nicer dry erase board like you have there. I'm feeling a little jealous of your setup right now. Okay. And as you probably heard about at some point in your life, the charge of a proton is +1, a neutron has 0 charge, and an electron has a charge of -1. We say that charge is quantized, but I'll write that up on the board in a minute. Think about how perverse nature is. It takes a big fat particle like a proton, and it gives it a charge of +1, and a little teeny microscopic particle like the electron, and it gives it a charge of -1. The masses of these two particles are not balanced, but yet their force of electromagnetism is. And nature is weirdly asymmetrical in that way, or at least she seems to be. Later, it's going to turn out that it's possible for nature to produce antimatter particles, the charge opposites. And sometimes nature, when she's feeling very naughty, she will create a big fat negative particle called an antiproton and a little microscopic positive particle called a positron or an anti-electron. But we'll talk about that stuff later. For now, forget about that. Most atoms we're going to deal with for the moment are going to be made of normal matter. So it's time to play a game, and that game is called Let's Build an Atom. All right. Let's build an atom. I'm going to give you guys the specs, and you're going to tell me what the atom is. This atom has an atomic number of 1, a mass number of 1, and it is electrically neutral. All right? Now, you know, this was a lot more fun in the classroom when I could just look for the person who's squirming and shifty-eyed as much as possible, and I could call on that person and force them to answer. Now you're all just little tiny faces on my screen. It's like you don't even exist anymore. So someone out there want to help me contribute to this discussion so I'm not just talking to myself in my bedroom here, and tell me what this atom would look like. I want you to tell me how many protons, neutrons, and electrons it has. You got all the stats. You got an atomic number of 1, a mass number of 1, and it's electrically neutral. Who's got this? Don't think because your video.
One single proton?
Is that Zach? Who is that?
Yeah,
Oh,
it is.
there's 2 Zachs. Right. Okay.
Yeah,
that
I'm
sounds
on a
like
computer and a phone.
Zach Salah. Okay. I'm sorry, Zach. Can you say that one more time? I was distracted.
One single proton?
Correct. And what else?
I don't know.
Well, the atomic number tells you it's 1 proton. What is the mass number telling us? According to your notes, is anyone taking notes here?
It's the number of nucleons in the atom.
Number of nucleons, says somebody. I can't see all your little faces at once. Yeah, okay. It's the number of nucleons. So what the hell does that mean then? How many neutrons do I have?
1 neutron.
False. Look, if I add 1 neutron to this atom, how many nucleons do I have?
And then it would be 2.
Wait, wouldn't it be 1 electron then?
Well, okay, yes. But let's just not, before we get to this, can we do this first? Just so we can stay logical? I just want to make sure that I didn't lose anybody there. The mass number of 1 means you get 1 nucleon. And you already used up your damn nucleon with this proton here. So there can't be any neutrons. Capiche? Okay, now whoever said that thing about the electron, yes. It's electrically neutral, and that means we have 1 electron. There's your atom right there. What's this atom called? It's a famous atom. It's got a name.
So I'm going to take a stab at it and say hydrogen, but I didn't, is it like an isotope?
Yes, you anticipate me, Sirrah. It is hydrogen, and it is a unique isotope of hydrogen that I want to talk about. So this atom is hydrogen. But this isotope of hydrogen has a particular name. I wanted to see if anyone knew what its name was.
Is it deuterium?
No, Kirill. Dew,
Okay.
like deuteron, is 2. This is protium. The most common form of hydrogen, 1 proton and 1 electron, is a special isotope known as protium. It's probably the most basic atom in all of nature. It's the most common atom in all of nature by far, by at least a ratio of 10 to 1. All right, let's try it again. I can see a few of you taking notes. That makes me happy. I'm going to erase. It's kind of harder to tell when you guys are done taking notes because I can't see everyone at once. So if you don't like my pacing, if I'm going too fast, feel free to shout out at me. Otherwise, I'm just kind of assuming that you got all this. All right, let's build another atom. Atomic number of 1, mass number of 2, electrically neutral. What's my atom look like?
It's going to be 1 proton.
I like it. That's our atomic number. Neutrons?
Could it be
Diana?
1 electron?
Okay, yeah, there will be 1 electron because it's electrically neutral. But Diana has
neutron.
pointed out with her sign language skills that that there's also going to be 1 neutron. What atom is this?
Oxygen.
No.
That's
Oxygen has an
deuterium.
atomic number of 8.
That's deuterium.
That's deuterium. But Kirill, I'm afraid they're going to miss the point. Yes, it's deuterium as an isotope, but we also
It's
learned.
still hydrogen, but with more neutrons.
Yes, because remember, our atom is defined by this guy, by the atomic number. So it is still hydrogen because the atomic number defines the atom, but it's a unique isotope called deuterium. Oops, I forgot my N. Deuterium is probably the most famous isotope in all of nature. And let me explain why. Here, I'm gonna get a lot of junk floating around here. I'm gonna show you guys something. Let's share a screen here. Share a screen. And let's go, I don't know, let's go to a cool place in space, Eagle Nebula. Let's find ourselves a gnarly picture of gas in space. Here we go. I like this one. Can I minimize all this? Yeah. So that's a small pictures suck. We all know that. Oh, here's a big one. Okay, so here's a beautiful, inspiring picture of the Eagle Nebula. And let's fly with our spaceships into this giant cloud of gas in space. And if we started sort of slurping up gas with our cosmic vacuum cleaner spaceship and counting up atoms, we would find of all the atoms in these gas clouds, 9 out of every 10 are in the form of hydrogen, 1 out of every 10 are in the form of helium, and there's hardly much of anything else at all. At least that's what I'm going to tell you now. So let's get back here for a second. If we went into the Eagle Nebula, or if we went anywhere in space really, we would find that if we counted atoms, so if we count gas atoms, we'd find 9 out of every 10 were hydrogen, and 1 out of every 10 were helium, And you'd have to count through hundreds or thousands of atoms to find anything else, like a carbon atom or an oxygen atom. Okay, here's where it gets more interesting. Let's suck up atoms in the Eagle Nebula, and let's throw away all the heliums, and let's just start counting through those hydrogens. Let's collect a lot of those hydrogens. You would discover that for every, I don't know, let's say roughly 6,000 hydrogens that you counted, 1 out of every 6,000 would be a deuterium. And these deuteriums are found all throughout space. They're kind of left over from the Big Bang. There's some actual cool fundamental physics going on with the origin of deuterium, but I might save that discussion for another time. This thing here is like a big deal in science. It's what's known as the cosmic abundance of deuterium. And this ratio of 6,000 to 1 is found not only in the Eagle Nebula in outer space, it's also found in the hydrogens in ocean seawater, in a cup of coffee that you drink in the morning, in comets that orbit the sun, in approximately the same ratio. It turns out that we know that the Big Bang is supposed to produce a ratio close to this amount of deuterium to hydrogen. So professional scientists actually measure ratios of isotopes to learn about the history of where water comes from and goes to throughout our universe. As a case in point, there was a pretty important mission. Let's share my screen here so I can show you guys some cool stuff. There was a famous spacecraft we built called the Rosetta Spacecraft. And its mission was to visit a comet for the first time and take samples of ice water at its surface. Okay, so come on, internet, work with me here. There we go. Here's the Rosetta Spacecraft. And the Rosetta Spacecraft was kind of cool. It did this orbital flyby of a comet. I needed some help here to pronounce this name. Comet Churyumov-Gerasimenko, and here's a picture of up close and personal view of this comet. This is, by the way, this picture's only a couple of years old, and it's totally amazing. If you're looking at this Comet Nucleus here, you can see the surface is dark and black, and most of this comet is actually made up of frozen water ice. The darkness that you see at its surface is because this lump of ice has been flying through our solar system for billions of years, and it's collected a lot of bits of carbon soot on its surface along the way. So you might think of this as the sort of dirty ice you see in the wintertime underneath your tires in the city. Anyways, these comets contain mostly water. And a big question scientists asked themselves was, could Earth's oceans be related to these comets? Is it that Earth started off without water and then comets slammed into Earth and brought ice water that way, and that's how we developed our oceans? Or could it be that, I don't know, perhaps water and then... Oh, I'm sorry? Oh, I thought I heard a comment. But in any case, another possibility was that volcanoes produce a lot of water when they outgas. So the two competing theories were either Earth has been sitting around for billions of years just pumping out water in its volcanic outgassing, or perhaps comets slammed into Earth. I guess I'm there. Anyways, here's a little artist illustration of what we did when we got the Gerasimenko comet. We actually dropped a little washing machine-sized probe onto the surface of the comet so that we could measure the ratio of the... Oh, hold on a second here. Can whoever the hell that is mute themselves? Because it's... Or I'm going to find you and mute you for you. Hold on a second. Who's making that chatter? Okay, whoever it was, they got themselves. All right, let me try this again. Let me share my screen. Let's go back to the comet here. Okay, so this is just kind of a cool story. This Rosetta spacecraft dropped a little washing machine-sized probe onto the surface of the comet, and it had some harpoons to kind of catch onto the comet and drill into the ice so that it could measure the ratios of deuterium to hydrogen. And they wanted to see if the ratio of deuterium to hydrogen matched what was in seawater. Unfortunately, the mission ran into some problems. Let's see if I can find, I'm just kind of going through Wikipedia here.
Wait, how fast was the comet going?
Comets typically travel around the sun with speeds of order 15 to 20 kilometers per second. That's like 20, 30,000 miles per hour. It's stupid fast.
And that thing was like able to somehow catch up to it?
It was, is that Thomas? Can I detect
Yeah.
I can tell by the timbre of your voice. Yeah, so Thomas, these comets are traveling super fast. They travel anywhere from 15 to 20 kilometers per second, which is ridiculously fast. So part of the thing, if you guys can still see my screen, the orbital dynamics of catching up to the comet was kind of complicated. They had to launch it from Earth. They probably did a couple of gravitational slingshots. They had to try to intercept this thing in real time. It's a miracle the thing worked as well as it did. And you can see the speeds involved here. It's kind of flashing through at the bottom, are somewhere between 15 and 20 kilometers per second. Now, the Rosetta spacecraft did catch up with the comet, and that part of it kind of worked flawlessly. What ended up failing is, and I have some pictures of this. Let me see if I can go to my S drive here, because I tried to grab everything before I had to leave CCRI. I've got some cool images here. I'm kind of wasting a bit of time on this, but it's kind of fun. I've got some cool images of the Rosetta comet and the spacecraft landing. For instance, here is a picture taken from the spacecraft of the little probe leaving the spacecraft and going down to intersect the comet. Here is a picture of the comet up real close. Unfortunately, because comets are much smaller than even moons, even tiny moons, the surface gravity of a comet is very low. Like, you could probably stand on this comet and jump in excess of escape velocity. So gravity is so weak that it only tenuously binds you. So the little washing machine was supposed to land on this ice, and it was supposed to fire harpoons into the ice to sort of latch onto the comet. But one of the harpoons got frozen, or it stuck, and it didn't fire properly. So the spacecraft, the lander, went bouncing across the surface of the comet, and then it landed in the shadow of some kind of a boulder, and it was flopped over on its side. So the scientists could see pictures from the probe of looking sideways out onto the surface of the comet, but the probe kind of could only complete some of its science missions. Apparently they managed to salvage it enough, and they tested and measured the ratio of deuterium to hydrogen in the comet ice, and then they compared the ratios of deuterium, hydrogen, and seawater, and found just enough of a difference that they ruled out comets as the source of providing enough water for its oceans. Why am I telling you this story? Because isotopes matter. Changing the number of neutrons in an atom is like a little scientific clue. It's like a little forensic science clue that we can use to study the history of our solar system. And in that sense, isotopes are interesting. Okay, so enough about that. And you, by the way, if you go to this Wikipedia page, you can read all about this comet and this lander. It's totally cool. Eventually today, before I burn up this entire lecture, which I've actually burned up a lot of it already, this is going slower than I thought. We're going to want to get around to talking about light. And to talk about light, I need us to take a look at how electrons work inside of atoms. So let's go back to our PowerPoint show here. I'm going to share that with you. And let's go ahead and let's take a look at our basic hydrogen atom together. So function F5, slide 12. Okay. You guys should be looking at a basic picture of a protium atom, a single proton and a single electron going around it. Let's try to take some notes about this here on our board. Okay, so we're going to do a little section of our notes called the energy levels of a hydrogen atom. And at the beginning of our tale, I'm going to begin with a single proton in the center of my atom. Okay. And a single electron in orbit around it. And if you were to ask me how far away does the electron orbit from the proton, I would say it's a very short distance by human scales. The distance from here to here is what's known as a Bohr radius. And a Bohr radius is a very tiny number. It's 0.5 angstroms or 0.05 nanometers. I don't know if in your class we've had a chance to define what either of those new units are. So these are units that we use for the very tiny world of atoms. Let's get a couple of conversion factors. So 1 nanometer is a billionth of a meter. Remember, a billion is a factor of 9 zeros. So a billion is 1 times 10 to the minus 9 meters. An angstrom is 1/10 millionth. And we're going to use both nanometers and angstroms in our spectroscopy lab or lesson today. 1 times 10 to the minus 10. In any case, it's a tiny little distance, but we're talking about atoms here. We're not talking about dump trucks. We're talking about little tiny things. The default orbit at 0.5 angstroms is what scientists call the ground state of the electron or the atom. And the ground state is the lowest or the closest possible orbit. The electron's not capable of getting any closer to the proton because of something called the conservation of angular momentum. And I had a jazzy demo to do with you guys there, but I sort of ran out of time before class ended, and I didn't want to take up any of today's lecture. At some point, I might want to do a little lesson with you guys on the conservation of angular momentum. In any case, the electron has trouble getting any closer to the proton than this. But it is possible for the electron to increase its orbital distance if it gets smashed into by another atom. Usually the way atoms exchange energy is atom number 1 smashes into atom number 2, but the atoms aren't faceless particles like these two moonballs here. They actually have internal structure. And when atoms collide with each other, their electrons can give each other a little kick, right? And so the electron's capable of getting up to some other orbital distances. Okay. If we think about the way gravity works in our solar system, we know that Earth orbits at 1 astronomical unit from the sun, and that's just because of the vagaries of how our solar system formed. But there's nothing in the laws of gravity that would prevent Earth from orbiting at some other distance. Like Earth could orbit maybe at 0.987 AU or 0.723 AU. But it's not so in the microscopic tiny world of atoms. In the world of atoms, we say that the electron orbits are quantized or restricted to discrete, unique distances. Let's take a quick note about that. So we'll say that the orbits of electrons are, here's a fancy $10 word for you, okay? They are quantized. And that's another way of saying that they are discrete or choppy. Or here's another fancy way to say that. We can even say that they were pixelated. In some sense, when you consider the microscopic world of atoms, you're actually getting down to the fundamental resolution of space itself. And just like you zoom in on a digital picture, you eventually discover that it's made out of unique, discrete pixels, each with a different color. In the microscopic world of atoms, we're getting down to the resolution of space such that the electron cannot orbit at any distance from the proton that it wants, but is constrained to unique orbital levels. The ground state, the lowest orbit, is sometimes given a principal quantum number. We call it n equals 1 for the first orbital state or the first orbit. And each orbit after that, which are prescribed at unique distances, have different quantum numbers. The second orbit is called the n equals 2 state. The third orbit is called the n equals 3 state. Now, the reason why they say state instead of orbit has to do with the fact that the electron isn't exactly a particle. It's not a dumb baby like this thing. It's actually some kind of an energy packet and has wave-like properties. But I ain't got time to get into all that. We're going to be here until we grow old and die. So let's just say for now that each one of these numbers represents a different orbit the electron can have. In a few moments, we'll talk about the properties of waves. Okay, now let me go back to my slideshow to show you guys a couple of things. You'll notice that when I try to represent this, hold on a moment here. I'm still working out my, where are all of your faces? Where is my control box? Share screen, slideshow. Okay. Function F5. Did that work? Nope. Hold on, guys. I just want to run the damn slideshow. Function F5. Okay. You'll notice if we try to draw an atom like this, we can draw the first orbit and the second orbit and the third orbit, but pretty soon our screen is too small to draw all the rest of the orbits. So rather than drawing all the orbits as big circles, we sometimes like to represent them in a more abstract way by what's called an energy level diagram. And this energy level diagram zooms in on a tiny piece of the orbit so we can see each orbital position as sort of like rungs on a ladder. This is what's known as an energy level diagram, and this in particular is the energy level diagram for hydrogen. Now, we're going to be measuring the amount of energy that it takes the electron to get from the lowest orbit up to these other orbits. So, okay, here we might want to do a favor for the students in the night class who weren't present for the discussion on energy. And maybe the daytime students can help us remember what we learned. Let's erase here. And let's have one of you guys with good memories remind me what the definition of potential energy is. In fact, I want to know about gravitational potential energy. Does anyone have that in their notes? This is for the nighttime students who are with us, who maybe didn't get potential energy defined for them. I thought one of you guys could help me and demonstrate your profound knowledge of physics.
Gravitational potential energy is energy stored in a gravitational field.
Correct. And the setup, Jillian, was I've got the ground, right? And I hold some test mass, like my 1 kilogram mass, some number of meters above the ground. And what was the formula for potential energy? It's expressed in terms of the height and the mass, and it's expressed in terms of little g. Jillian or anyone, do you want to tell us the formula?
Potential energy equals mass times little g times height.
Okay. And y'all remember about little g, right? What the hell's little g? Give me some of that little g.
The local gravitational constant?
Local gravitational acceleration, which is also a constant, but it's a constant for Earth, not for Mars, right? I just don't want you to confuse little g and big G. Little g has a value of 10 meters per second squared. And it's the local acceleration of Earth's gravity. What units do we measure energy in, students? Students who love energy more than they love life itself?
Joules.
Joule.
Joules. Thank you.
Damn it, I tried to get my mic on before that.
Oh, or someone, wait, Diana, was that you?
Oh yeah, I was trying to race to turn on my mic so I could say joules, but I was too late.
Yeah, well, this whole video chatting thing is weird for all of us, but it's not unpleasant, really. Okay, so we measure it in, if you guys think about the units of potential energy, right? Potential energy is a mass, which is a kilogram, times acceleration, meters per second squared, times a height, which is a meter. And if you smush all these units together, you get kilograms times meters squared per second squared. Let's move my thing down so you can see that. Now look, kilogram meter squared per second squared is an annoying thing to say, kilogram meter squared per second squared. That's why we have renamed this bad boy the joule, okay? So the joule are our MKS units of energy. Now, joules are fine when you're working with the world of large objects, like this here, 1 kilogram test mass. Does anyone remember when I lifted the 1 kilogram test mass 2 meters above my head? How many joules of energy was that, Diana? Oh, shit. Boy, you regret raising your hand now, don't you? How many joules of energy does it take to lift a 1 kilogram mass 2 meters over your head? I need my other meter stick, so you guys look that up. Come on.
$20
Oh yeah, right there.
How many joules was that?
20.
20, that's right. So here I go.
Yeah, under the 1 kilogram squat.
It was a 1 kilogram squat, right? 20
Yeah.
joules if I put this thing 2 meters above my head. That's about reaching my hand up as high as I go. Okay. Obviously, joules are a hideously inappropriate unit of energy to use when we're working in the microscopic world of atoms. So allow me to use a unit of energy appropriate for the tiny world of atoms called the electron volt. Now, when we're dealing with the world of atoms, we're not dealing with the force of gravity anymore. We're dealing with the force of electromagnetism. You guys will remember that the force of electromagnetism has to do with charge. And when we lift and lower electrons inside of an atom, we're not changing the gravitational potential energy. We're changing what's called the electrostatic potential energy. But in some sense, it's not too much different than when you lift a 1 kilogram mass up in the gravitational field of Earth. And that's because the electron wants to be attracted to the positively charged nucleus. And it's a force very much like, well, not like the force of gravity, but similar to the force of gravity. It's related to charge instead of mass. And when you lift this electron up in the field of the atom, you are giving it more potential energy. The quantities of energy are smaller because the atoms are smaller. And in that sense, a joule is a not very appropriate unit of energy to use to measure these electrons. Instead, we're going to measure the potential energy of an electron in a unit called electron volts. An electron volt, you don't have to really understand what it means. You just have to think of it as a tiny packet of energy. And it has a value of 1 electron volt is roughly 1.6 times 10 to the negative 19 joules. Go ahead and write that down. We're going to need that for our homework session this week. Okay. Now, from time to time, atoms can become energized, and the electrons can lift themselves up in this atomic energy field. And what happens is usually it is the collision of atoms that cause electrons to jump from low to high orbit. And once they do this, let's draw a little picture. You can find yourself with an electron. Let's put our electron up here in the n=3 orbit, where it will hover in an excited energy state for a period of time of approximately, I don't know, maybe 10 to the minus 8 seconds or so. That's a long time for an atom. Are you having trouble reading that, Diana?
Yeah, a bit.
Let me try to improve that.
Much better.
Delta T here represents the length of time an electron spends in one of its orbits. It's just a number for fun. You don't have to memorize it. 10 to the minus 3 seconds. I'm trying to impress upon you guys that time scales for atoms are much different than the time scales over which our lecture is taking place, right? An electron can hover in the n=3 orbit for 10 to the minus 8 seconds, and that's enough time for it to orbit around the proton like 40,000 times more. So imagine like 40,000 trips around the sun. That would be 40,000 years for Earth, right? That's sort of the equivalent of what we're talking about. 10 to the minus 8, wait, I wrote 10 to the minus 3, sorry. 10 to the minus 8 seconds seems like a short time to you, but we're talking about atoms here. That's a long time for an atom. Eventually, the electrons get tired and they desire to drop down towards their lower energy states. They only spend so much time hovering up here in the excited orbits. And eventually they're going to drop down to a lower orbit. And when they do so, they are going to need to release electrostatic potential energy. But how do we release energy inside of an atom? Well, let's think about the equivalent here on Earth. If I take a ruler and I give it some potential energy and I lift it above the ground, now this might not be 20 joules, it's some other number of joules, and then I were to drop the ruler, you guys can hear that the potential energy of my ruler is transformed into a sound wave. I don't know if that sound actually made it through the computer screen or not. It's kind of a better demonstration when you do it in class. Okay, some people are nodding yes. So it turns out that if you had some kind of a decibel meter, if you had a sound meter and you measured the energy of that sound wave, you would discover it was exactly equal to the potential energy of lifting this ruler about a meter up into the air. So when I drop my ruler in a gravitational field, the energy gets transformed into a sound wave. It's the crashing of the ruler into the ground is transformed into a. In this microscopic world of atoms, energy is also going to be released, but not in the form of a sound wave, but in the form of a light wave, a microscopic particle of light known as a photon. And usually people represent it like so. We have, let's use a colorful marker here, a little wiggle coming out. And this little packet of energy is called a photon. A photon is your fundamental smallest unit of light. And this is going to transition us for the rest of our lecture time is almost up here. Let's just take a couple more notes and then we'll stop it and we'll figure out how the hell we're going to do our labs. Okay. So I'm going to erase and I'm going to take a couple of notes about light. First of all, let me show you my slideshow for a moment. Let's see here. I need to share screen. Just go to my slideshow and function F5. Okay. It's too bad. In class, when I have the projector, I often do this demonstration in class where I take a prism and I break light up into its component waves. But I tried very desperately to get that going here this morning, and I will be able to show you a version of it, but I couldn't do it with the prism, and that made me very sad. What I want to do is just show you a physicsy model of what light is. Light is called an electromagnetic wave. And the wave is made up of a sort of a two-part martini here. One part is the electric field. You might think of the electric field as similar to the thing that makes sparks when you take your socks out of the dryer. It's a sort of static electric field, or it's related to static charges. But electromagnetic forces can produce two types of energy fields, electric fields and magnetic fields. And light is a combination of both. You'll notice that the electric field, shown in blue, is kind of oscillating in a vertical direction, and the magnetic field is constantly perpendicular to this, and it's oscillating in a horizontal direction. That's a hallmark of light. It's got two components, an electric field and a magnetic field. Obviously, that picture is kind of tough to draw on the chalkboard unless you have some really talented art skills. Let's just take a couple of notes about this. Light is an electromagnetic field, or it's a wave in the a wave of electromagnetic field. And it's got one part is the electric field. The electric field we associate with static charges. And you'll learn more about that in time. Another part is the magnetic field. And that's associated with moving charges. The magnetic fields and the electric field are both produced by the force of electromagnetism. But there's a very slight difference between the two that I don't have time to get into. Light waves can be continuous. They can also be contained in small packets called photons. So a photon is a tiny packet of light. I've intentionally used the term packet so that I don't get hedged into saying particle or wave. Light has both particle and wave-like aspects, and I'll probably do a demo on this next time. But for now, what I want us to do is take down some notes about the properties of waves, and I'll show you a couple of slides to help you understand this. So let's talk about the properties of waves, and then we'll look at some cool pictures. Waves have properties like wavelength. Now, the symbol, let me get a little closer here, so this isn't too difficult to read. The symbol for wavelength that we use in physics is the Greek letter lambda. Lambda kind of looks like an X that's missing an arm, okay? And wavelength is the distance from crest to crest of our wave. And it's a real physical length. It's a repeating oscillation or cycle. And we measure it in units of either meters or nanometers or angstroms. Sometimes certain astronomers even use microns if they work in the infrared. Another property that waves have are frequency. Frequency is going to get a curvy F, and it's measured in units of cycles per second. Let me see if I can show you guys a little illustration here of the difference between wavelength and frequency. I'm going to try to do something. I'm going to share my screen, and I'm going to see if I can call up those physics Java apps. Let's see if I can do this here. I used to have these pretty jazzy physics Java apps. I don't know if they're going to work on this laptop. I'm going to, in the S drive, here we go. Let's try the radiating charge app and see what happens. Attempt to view. Shit, why is this thing blocked? Don't block my thing. Manage. Block sites. Can you guys see what I'm doing here? Because I don't know. Block sites from running Flash. Ask first. Allow. Okay, let's try that again. Let's see what happens if I try to run that. What? Allow. Okay, cool. Hey, can someone just unmute and tell, can you see this thing that I've got here on my screen?
Yes.
Cool. All right, thank you. Okay, what you see here is a proton. And a proton is surrounded by an electrostatic field. What the hell is an electrostatic field? Oh my God, we don't have time for that today. Let's just think of it as the essence of charginess that surrounds our proton. Now, the field itself is not light, but light are ripples in this electromagnetic field. So I'm going to take my proton and I'm going to give it a little wiggle here. And as I wiggle it, you can see little waves radiating off from my proton. Now, this is light. Light are ripples or waves in the electric field. Now, I was kind of doing this chaotically. That is a form of light. Let's give this a nice sinusoidal oscillation. The amplitude is how high and low the charge is wiggling. I'm going to lower my amplitude a bit, but I'm going to increase my frequency. Frequency is measured in cycles per second. And it's the number of wiggles per second that this little proton is doing. Let's increase our frequency and see what happens. You can see that the proton's shaking faster. That's kind of some trippy shit to look at there. It's going to give you guys nightmares or at least some psychological brainwashing. Okay, which is what science and all of education really is. Okay, so let's get out of here for a second. I want to show you guys another thing. I want to show you a more sophisticated model of an electromagnetic wave. And here, this thing is a, where's this thing here? Here we go. Oops. Okay, this is a pretty sophisticated model of an electromagnetic wave. Here, the electric field is shown as little green arrows, and the magnetic field is shown as blue arrows. And these are what mathematicians call the vector field. And, you know, vector fields are complicated. They have direction as well as numerical value. But you guys can clearly see that there's a wave or some kind of a ripple going past you. Now, the wavelength is the actual distance from crest to crest of this wave here. And it's measurable in meters or it's measurable in nanometers, depending on what type of a wave you're dealing with. The frequency measures how many cycles per second go past your wave. So let's try to count the frequency of this wave. I'm going to start when it hits my cursor. 1001, 1002. Oh, shoot, I lost my cursor. 1001, 1002, 1003, 1004, 1005. So you guys will notice it took 5 seconds for a wave to go past a certain point on my screen. And that means the frequency is probably 1 cycle every 5 seconds. Let's go ahead and look at this here on my chalkboard. And yes, I'm going to stop soon, but let me get to a good stopping. Frequency can be kind of weird the first time students learn about it. It's a number of cycles per second of my traveling wave. And cycles are not a real unit, they're kind of a dummy unit. So the actual units of frequency are 1/seconds. You should probably think of it in your head as cycles per second, but you write it as 1/seconds. The cycles are like conceptual, they're not a real physical unit. Because 1/seconds sounds really weird and kind of crappy your first time around, people have renamed the per second as a hertz. So units of frequency are either cycles per second, per seconds, or hertz. All of those are saying the same thing. The third property that waves have, besides wavelength and frequency, is they also have energy, which you already know about. We can measure the energy E in either joules or in electron volts. One of the first people who did experiments in light was none other than our homeboy, Sir Isaac Newton. Sir Isaac Newton is most famous for his laws of motion and his laws of gravity, but he also did extensive experiments in optics, including this experiment, where he sent a beam of white light through a triangular piece of glass called a prism, and he could separate the prism into a bunch of colors. And these colors are what is known as the continuous visible spectrum. Your eyeballs are sensitive to a narrow range of light that goes from 400 nanometers, which you call purple, all the way up to red light around 700 nanometers. You call that red. Purple's at 400 and red is at 700. Now, the order of the colors of the continuous spectrum is always the same when you make it with a prism. It depends which direction you angle the prism, but you can get one or two orders of colors. In one sense, the order of colors goes red, orange, yellow, green, blue, indigo, violet. It's an acronym which scientists memorize as Roygbiv. I personally dislike Roygbiv because I don't like having the longer wavelength light on the left-hand side. I prefer the less catchy but weirder acronym, BIB-G-YOR. So red on the right-hand side has a wavelength of about 700 nanometers. And all of this will be contained in the PowerPoint slideshows that you can download. Purple or blue has a wavelength of about 400 nanometers. And it's not a bad idea for you guys to start memorizing that green light has a wavelength of about 500 nanometers. I'd also like to make mention that in Sir Isaac Newton's day, let's share that screen again. Doing the best I can here, guys. When Isaac Newton referred to the color blue, when anyone recurred to blue in Isaac Newton's day, they referred to this kind of cyan or sky blue color. That's what was meant by blue. Here's a color that today we refer to as dark blue, but in Isaac Newton's day, this color here was called indigo, right around 450 nanometers. Indigo is a much cooler way of saying dark blue. There's a whole Wikipedia page you can read about it. I've got a personal crusade to bring back the color indigo, so let's all work on that together. You know, the visible spectrum that you see with your eyes is just one smaller part of a much larger totality of all the different types of light that exist in nature. Hold on, I don't know what you guys are looking at here. Share screen, slideshow. I want to introduce you to a friend of mine. And I think this is probably going to be our last topic of the day here, called the electromagnetic spectrum. The electromagnetic spectrum is the totality of all the different types of light that exist in nature. You guys might think of this as sort of like the periodic table of the elements, except it's for light. And your eyeballs are sensitive to honestly a pitifully narrow range of electromagnetic radiation that goes from 400 nanometers purple to 700 nanometers red. But there are other types of light that are basically the same as visible light, it's just your eyes can't detect it. When wavelengths get longer than 700 nanometers, all the way up to 1,000 nanometers, which we call a micron, you enter a region called the infrared regime. This is what cooks your toast in a toaster oven, or it's the type of light that comes out of a remote control when you turn on your TV. At even longer wavelengths, light turns into radio waves, which are very, very long wavelengths very, very low energy light that we use to communicate with our cell phones. At the shorter wavelength end of the electromagnetic spectrum, we have ultraviolet light. That gives you a sunburn at the beach. Shorter than 10 nanometers, we have X-rays, which are very tiny, short wavelength light, very harmful to you, that we use in medical imaging. And then after like 1/100th of a nanometer, you get into the ultra short wavelength gamma rays. This is the kind of stuff that comes out of nuclear explosions and nuclear reactions. And these can mutate your cells and turn you into a teenage mutant ninja turtle. So all of this stuff is the same stuff. It's light, but by changing the wavelength of light, you dramatically change how this stuff behaves. Now, in a moment, we're going to attempt to do a lab. I have no idea how that's going to go because I've never run a lab from my computer before. I do have a prism here. And this prism is capable of breaking white light into its component wavelengths. I wonder if I could shine some right at the camera. That would be pretty cool. I thought I saw it for a second. I wonder if I could do this. In any case, what? Can you guys see the rainbow? I can't believe I actually pulled this off. Pretty dope, right? This is the same experiment that Newton did. It'd be cool if, it helps if you get a really, really bright light. All right, well, you got a little bit of rainbow. This here is a tool called a spectroscope. And a spectroscope doesn't use, a rainbow. It uses this thing called a diffraction grating. A diffraction grating is sort of what you see at the back of a CD, like a compact disc.
Brandon,
Yeah?
I keep losing you. I don't know if you're getting too close to your microphone. Is
I think I'm
anyone
getting-
else? Is anyone
I think-
losing him?
Yep.
Yeah,
Yeah.
sometimes.
Yeah.
Oh, wow. Yeah, there's a lot of nods there. Tina, I think what happens, I have to keep remembering this. If I get too close to the camera, it actually picks up the audio worse. But as I get excited, I feel myself moving towards the camera, so I've got to hold back on that. All right. Look, why don't we do this? Before we start our lab, I thought you guys might want like a couple of minutes of break just because you've been listening to me for a while. So we're going to do a lab. It's going to be shorter than your average lab, but I need you guys to do a couple of things. First of all, I need you to download the spectroscopy handout. So I know some of you already have lab books. If you have your lab books, you can just use your lab from your lab book. Let me share my screen with you guys. Share screen. And you guys will notice in Blackboard here that if you go to the side, hold on a second, where it says lab, I've got a spectroscopy lab for you guys. And if you click on that, it should have spectroscopy.pdf. Some of you already have this in your lab books, and you're welcome to use that as well. So what you're going to want to do is you're going to want to print out that one page. It's a little spectrogram, or tear it out of your lab books. Now, let's say you don't have a lab book, and let's say you don't have a printer. You've got two options. One is to download the paper and try to draw on it with MS Paint. The other one, Newton made Pink Floyd. All right, I love this. Okay, sorry, I'm just finally reading the chats. I've been talking, so I couldn't chat with you guys. If you have some crayons or some colored pencils in your apartment, cool, grab those. If you have colored anything, we're gonna make a few colored lines. I'm basically gonna show you some stuff and you're gonna make some colored lines. So why don't you take like a 5-minute break or so. It's 1:03 on my computer. We'll come back at 1:10 and we'll start the lab. That'll give you guys a chance just to take a break and get a cup of water. And then I'll try to keep the lab to like 30 minutes or so we don't crush ourselves. We'll see how long it takes. Everyone sound like a good plan? Can I see some thumbs up? Everyone likes this plan? All right. Oh, by the way, do you guys know what we're going to try to submit this by Blackboard? So once you're done with the lab, the idea is you kind of color in the lines where I tell you to. I'm going to hold my phone up to the thing. And then you'll be able to submit it through Blackboard. I'll explain it when the time comes. Let's just take a break,
So,
okay?
How do we actually do it? The lab.
I'm going to try to show that to you because I had to figure this out with Jillian last night. I should be able to show you by sharing my screen at the end of lab. Does that sound good?
Okay.
Word.
All right, we'll try it anyways. This is a learning experience. So let's just get back together at 110 on my screen here, okay? Take a
Can we
5-minute
just,
break.
like,
Oh, Thomas, what?
can we just like stay in the group chat? Or
Everyone
all
can
right.
stay in the chat window, that's fine. I just want to I want to get my colored pencils and a drink of water, okay? That's all I need to do.
Yo, cat crew, it's adorable.
I expected way more tired faces.
I did too. And I'm one of them. That's why I'm not showing my camera.
Shit. Okay.
This went better than I thought.
Like in the lab book, what page or what chapter is it? Is it the 11?
11-5.
Whatever.
11-5. Yep.
Okay.
And remember, I have that available to you as spectroscopy.pdf right on Blackboard.
So, how does everyone like their quarantine?
I was gonna get Animal Crossing New Horizons, but I left it at my fucking friend's house.
Oh no, dude, it's worth it. Definitely pick it up.
Oh no, I want to, but I don't have my damn Switch.
My first class was public speaking. The whole entire time I was just playing that.
I've been playing Animal Crossing as we speak.
My friend's dropping off my Switch in a plastic bag.
That's respect right there.
I'm just bored out of my mind, like, and have been these past 2 weeks. It's awful.
When Thomas first popped up and I saw the Pikachu, I kind of laughed.
Yeah, I
know it was
I
good.
couldn't help but giggle there too.
Had to get the custom background going.
Is it a green screen?
Nah. It would be way better if it was a green screen. I lost my green screen.
Rip.
Yeah. I left it out like some function or something.
Breasts and pepperonis.
It looks like Thomas is using like one of those cool backdrops. I heard you can do that with Zoom, but I haven't figured it out yet. I'm going to test out this feature of my phone, which is, this is supposed to let me share my screen with you guys.
I'm going to take it, this isn't the lab I want to be colorblind for. This is where color blindness actually starts to be a detriment.
It should be okay.
The colors that's going, just those, the Vidgior, that should be fine.
Yeah, I mean, what's going to happen is we're going to do it all together. I'm going to be holding my, well, I've got to get my iPhone thing to, I've got to get my iPhone app. Normally, you're supposed to be able to go into the iPhone with your Zoom. I should be able to zoom you guys right to my screen, and it's failing. So I may have to restart this entire chat. Intro vid is my mood. Okay. Sorry, I'm just reading all your damn chats here. This is really funny. All right.
Yeah, by the way, Mr. Britton, sometimes when you head to the left, I can't hear your audio at all.
All right, I'll try to stay front and center.